So in terms of graph behavior, we talked about increasing and decreasing. In this video, we want to talk about concavity, which has to deal with the curvature of the graph. So there's concave up and concave down. If we imagine our two types of parabolas, so we have the parabola that opens upward, and we have the parabola that opens downward. If something has the shape of a parabola opening up, that is concave up. So you can notice in terms of the behavior is that our function is decreasing, and then it reaches this kind of local minimum, and then it starts increasing. It also kind of looks like a cup, like if it was raining, it would hold water in it. That would be concave up. There's kind of two parts to it. There's this decreasing side, but the curvature of our graph, the curvature is up. And then we have this increasing part of our graph also where curvature is upward. Now, the other case, when we have our parabola opening down, this overall shape is concave down. So with this, it's changing from increasing, reaches a local maximum, and then starts decreasing. So in this increasing section, the curvature is going downward. How I can think of this is like, it's kind of shaped like an umbrella. If it was raining, it wouldn't hold any water, it actually repels water. Whereas with concave up, if it was raining, it's acting like a cup, and it would collect water. So concave up and concave down can show up in our graphs, and as we see in this graph down below, we can be mixing concave up and concave down together. So we're going to touch on these ideas as well as tying in our increasing and decreasing idea, as well as this piece about an inflection point, which is when we switch concavity either from up to down or down to up. So we have this graph here that is a polynomial. It's coming from negative infinity, it increases up, and then at 2, 8, it switches and starts decreasing down to coordinate 6, 4, and then increases off to infinity. So some questions we want to answer. Let's first look at these A and B of where is our function positive and where is it negative. So this is the equivalent of asking where is f of x more than 0? So where's our function positive? And where's our function negative? So where's f of x less than 0? So what's going to separate these positive and negative f of x values is our x-axis. So anything above the x-axis, that's where f of x is positive. Anything below the x-axis, f of x is negative. So if we follow our function starts negative because it's coming from negative infinity, and then it switches at x equals negative 2. So at x equals negative 2, our function is actually equal to 0. So we're switching from negative to positive. So we want to state the interval, and this could be multiple intervals, like if we dipped back below the x-axis, then we'd have another interval that was negative. But this one, after x equals negative 2, our function just stays positive. So we're starting at negative 2, and it stays positive as x goes out to infinity. We always use parentheses with infinity. We're also going to use parentheses at negative 2 because it isn't positive at exactly negative 2. Again, it's actually 0 there, but just to the right of negative 2, then it starts to be positive. And in terms of negative, it's for all x values from negative infinity up until negative 2. So from negative infinity up until negative 2, again using parentheses because we don't want to include those endpoints. All right, increasing and decreasing. So we talked about this in the last video, but let's get some review here. So we're starting at negative infinity and going up to this coordinate 2, 8. So all the way out from negative infinity until we reach x equals 2, So we have this turning point at x equals 2, or we could think of that as a local maximum. at that coordinate. But between negative infinity and x equals 2, our function is increasing. And then it switches until we get to this coordinate 6, 4, which is a local minimum. So from positive 2 until positive 6, our function's decreasing. And then our function goes off increasing to positive infinity. So in terms of where is our function increasing, what we see from that is we start at negative infinity and go to positive 2, again only using parentheses because we don't include those endpoints, and a union with starting at 6 and going off to positive infinity. Then for decreasing, it was just between 2 and 6, so we're going to have this interval 2, 6 using parentheses. All right, concave up and concave down. So what we're looking for is curvature in our graph. So if we had any part of our graph that was linear, linear graphs don't have any concavity to them. But with these, if we kind of zoom in and look close, there's always curvature. This rate of change isn't staying the same. So looking at our graph, we can see our function is increasing and then it switches to decreasing. That behavior there, that's concave down. And you could see, like if you imagine this parabola that opens downward, even though it doesn't fit perfectly, it overall has that shape of a downward parabola. So we have increasing to decreasing, so we're seeing concave down. But then we can see we have this other switching point of where we're going decreasing to increasing, which is our concave up shape. So we have a section of our graph that's concave down and a section of our graph that's concave up. So there's this point where it's switching. Typically, this isn't always the case, but typically if you have this local maximum and local minimum, it's typically halfway between them. So we have this x equals 2 local maximum, x equals 6 local minimum, so halfway in between would be at this coordinate 4, 6, and this is the inflection point. So if we zoom in on this point, and it's going to be very, very, very subtle, or right close to this point, but the idea is this curving down, and then once we switch this point, it starts curving upward. So visually, we're getting this curvature, and it's a change in curvature of opening downward to opening upward. So this inflection point is going to separate where our function is concave up and concave down. So to the left of x equals 4, that's where our function was concave down. And to the right is concave up. So we want to describe these intervals. So for our function to be concave up, that was starting at positive 4 and then going off to infinity. Our graph is continuing to be concave up. And what intervals for concave down, that was from negative infinity up until 4. Now with those, and we don't want to include 4 itself because technically at that inflection point, it's neither concave up or concave down. It's switching between the two. So there's no concavity there at that inflection point. All right, our last question here is to find any inflection points. And just keep in mind that this is a coordinate. That's what can be tricky about this graph behavior section, is switching between interval notation and coordinate notation because they look exactly the same. Like if we go back to part D here where we were looking where our function's decreasing and we have these parentheses 2, 6, really what we're saying there is this interval of 2 is less than x is less than 6. It's not a coordinate. It's not x and y. It's an interval of values. So you just want to be careful switching between the two. So finding an inflection point or finding local minimums and maximums or absolute minimums and maximums, you're answering with an xy coordinate on the grid. Whereas all of these with positive, negative, increasing, decreasing, concave up, concave down, All of these are being answered in interval notation describing values of x. So our inflection point we found was at that coordinate 4, 6. So this is our 4, 6, which is representing a coordinate where x is equal to 4 and y is equal to 6. But I just like to call out where this notation can look exactly the same, but we are representing different things. Some are intervals, some are coordinates.